This is Dr. J. Mohan. I am from AC Department, Institute of Aeronautical Engineering. Today, we are going to discuss about Laplace transform, session 2. This under the topic of signals and stochastic processing subject. Today, the presentation outline is initial and final value theorem. First is initial value theorem, second is a final value theorem, then relationship between the Laplace transform and the Fourier transform. Difference between the Laplace transform and the Fourier transform. Then Laplace transform, some examples, then we go for the reference. We will see. First, initial and final value theorem. The Laplace transform of an unknown function x of t is known that it is possible to determine the initial and the final value of unknown signals. That means it's going to satisfy for the initial as well as a final value of unknown signal also. It's doing the process using the Laplace transform. First we go for the initial value theorem. The x of t is a continuous time signal and it is first derivative of Laplace transform. Then the initial value of x of t is given by x of 0 plus equal to limit s tends to infinity s x of s. Then final value theorem, the statement is if x of t is a continuous time signal, even though this is represented as a derivative, it is a first derivative of Laplace transform. Then final value of x of t is given by x of infinity is equal to limit s tends to infinity s of x of s. Now this case, the initial value theorem in the sense, it's going to start with the signal as a 0, even though that signal is represented as a 0 plus. And the final value is represented as a infinity. Both it will be going to respond with the derivative equations. The derivative is represented as a first derivative of both initial as well as a final state. If we do for the Laplace transformable case of first derivative of signal is represented as a limit s tends to infinity s x of s. And final value theorem state that limit s tends to infinity s x of s. Then we need to prove for the initial as well as a final value theorem of Laplace transform. First we go for the initial value theorem. The initial value theorem of Laplace transform enable us to calculate the initial value of signal x of t. So this signal x of t I consider as a x of 0 is directly from its Laplace transform of x of s without the need for finding the inverse Laplace transform of x of s. Then statement is the initial value theorem of Laplace transform, it's going to derive the first derivative of the signal. As per the statement of Laplace transform, we take for the Laplace transform of x of t, that is a continuous signal, in the derivative of n number, the value is equal to x of s. So we studied s is equal to sigma plus j omega. Sigma is represented as a amplitude in the real value. J, that is omega, is represented as a imaginary value of our s domain. So this s we call for the complex value. Okay, because of this have the real part as well as the imaginary part. So here I mentioned for the x of t, the Laplace transform is equal to x of s. If you take for the inverse Laplace transform, we got for the x of t. Now we know this is x of s is equal to, the formula is minus infinity plus into x of t e power of minus st dt v root. Okay, that means this is Laplace transform of x of t. Okay, this form I wrote like this one. So the Laplace transform of x of t equal to, that is we take for the both the direction of arrow mark, Laplace transform x of s, right? I write here. Then come to the point of our statement with the initial value theorem. When t tends to 0 in the limit x of t, okay, so that means if t equal to 0, then x of 0, so this represent as a limit. I should represent as a limit of t tends to infinity of x of t. So this portion, this means it's represented as an initial value. That means that t equal to 0. So that is produced the output is represented as a time domain is called for the x of 0, that is equal to limit s tends to infinity s of s. This is we call for the initial value theorem. Now we need to prove for the initial statement. We know the Laplace transform definition of an unilateral Laplace condition. So this unilateral in the sense we consider for the signal, that is the t is present for the minus infinity to plus infinity. So this minus infinity plus infinity 0 to infinity. We take for the only one direction, that is called unilateral. Okay, this means the unilateral means the signal will be going to start 0 to infinity. That signal we do for the Laplace transform. The Laplace transform of unilateral signal x of t, I write as a x of s. So this is x of s. That value is equal to the integration of 0 to infinity. Previously, what we are going to take in for the t is present for the minus 50%, even though the unilateral we take to prove for the initial value theorem, in the sense we should take for the 0 to infinity only. This is x of t e power minus st dt is right. Okay, this equation I write for here. This is unilateral. If bilateral, in the sense the this 0 it will be going to change with the infinity. Okay, mostly the Laplace transform we are going to dealing with only unilateral. Okay, then after taking the differentiation on both sides, okay, so what I am doing, the differentiation with Laplace transform, I write for the, I take for the d by dt of Laplace transform, this term. So the d by dt, the t term where is that, the automatically this derivative it's moved. So here how it will be going to move here. So that is LT is represented as a domain. LT represented as a domain. So now this value LT we take it out, d by dt of x of t. I put for the bracket. Now I should write for like this one. So that will be taken for the derivative. That's why 0 to infinity d by dt x of t. Here x is that. That's why I represent as a d by d. E power minus st dt is that. Okay. Next case. By the time differentiation property we know well. That is called differentiate with x of t dt in the Laplace transform is equal to s x of s minus x of 0 minus. So this x of s is represented as the Laplace transform. This one is represented as the initial condition x of 0 minus of Laplace transform. Now I should write for this case. Laplace transform of d by dt x of t is equal to integration of 0 to infinity d x of t divided by dt e power minus st dt is equal to s x of s minus x of 0. Okay, s x of s minus 0. Because of we know these terms, that is first derivative of Laplace transform the case. Now I taking for the s tends to infinity on both sides. Okay, so I take for the limit s tends to infinity on both sides. Then we should apply for the s tends to infinity for left side as well as the right side. Okay, so this case what will be happen? So now I take for the derivative of this value and I take for the resultant value of Laplace transform. Limit s tends to infinity, integration of 0 to infinity d by dt x of t e power s t dt is equal to limit s tends to infinity s x of s minus x of 0 I write. Now this term is represented as 0. Okay, integration, if you substitute limit and s tends to infinity, all it will be represented 0. Then 0 is equal to limit s tends to infinity s x of s minus x of 0 I write. Now, so this is 0, I take it, this x of 0, I take it out for the left side. Automatically what will be happen, this minus is getting to plus equal to limit s tends to infinity s x of s we got. Okay, therefore we have limit t tends to infinity x of t is equal to x of 0 and s tends to infinity s x of s we write. The first derivative of x of t and then the first derivative of x of t automatically consists of our initial value statement. That means x of 0 is equal to s tends to infinity s x of s. Now we take for the one numerical example. Okay. Then this numerical example, I take for the first derivative of x of t and then verify the initial value theorem of the function given by x of s equal to 1 by s plus of 3. Okay. So here I taken for the this as per the statement of our equation, our statement of our initial value, this notation x of s we taken. Now, if we go for the solution, I take for the x of s equal to 1 by s plus 3, taking the inverse Laplace transform of x of t. This x of s I take for the inverse Laplace transform. If we take for the inverse Laplace transform, we got for the x of t. Okay, that is inverse Laplace transform of x of s equal to x of t. Okay, so this condition we need to prove. The x of t is equal to inverse Laplace transform of x of s equal to inverse Laplace transform 1 by s plus of 3. So inverse Laplace transform of 1 by s plus 3 is equal to e power minus 3t. So as per the Laplace transform of inverse 1 by s plus of a, you take for this equation, this equation is equal to x of t, that is x of t equal to e power of minus at u of t, that is unidirectional that case. So now you take for this formula Laplace inverse transform of 1 by s plus a is equal to x of t, we got that x of t is equal to e power minus at u of t. So instead of a, here we received for the 3. So that's why x of t is equal to e power minus 3t. This is e power minus of 3t we write. Now we come with the point we adopted for the initial value theorem. Therefore, the initial value of the function is x of 0 is equal to x of t, t tends to 0. Okay. As for the initial value theorem, what is that? X of 0 is equal to limit t tends to infinity x of s. Okay. Into s we wrote. This is called for the initial value theorem. So we need to make for that one. That's why what I'm doing, we have for the x of t, then you substitute for the t equal to 0. Automatically it's converted for the x of 0. So here I need for the x of 0. That's why x of t, t tends to 0. We got for the x of 0. Okay. Here we got x of t e power minus 3t we received. Then the t tends to t is equal to 0. What will be happen? E power 0 is equal to, that is e power minus 3 0 equal to e power 0. That is value equal to 1. Then we write this. By the initial value theorem, we obtained x of 0 is equal to s tends to infinity s x of s equal to limit s tends to infinity s 1 by s plus of 3. This x of s we received for the 1 by s plus of 3. Okay. Now I make to write limit s tends to infinity as per the x of 0. I take it out for the s. If you take it out for the s from the 1 by s plus 3, then what will be happen? I write for the s, we take it for the 1 by s into 1 plus of 3 by s I wrote. This s cancel, I write here. So limit s tends to infinity 1 by 1 plus of 3 by s equal to 1. The initial value theorem is verified for the given function. So what is it? S tends to infinity in the sense this is getting to 0. 1 by 1 plus of infinity, that will be represent 0. 1 by 1 equal to 1. Okay, this is 1 by 1 equal to 1. No. Now this value, what we are going to find, x of 0 is equal to 1. At the same time, the x of 0 equal to limit t tends to infinity s x of s. This value also 1. Now both the values are 1, that is x of 0. Okay, this x of 0 equal to x of 0. This is t tends to 0 condition. Now the theorem was proved. This both values are equal. That's why the theorem was proved. Okay, this is called for the initial value theorem numerical example. Next, we go for the final value theorem. The final value theorem of Laplace transform enables us to find the final value of function x of t. So the final value in the sense it will be represented for the infinitive. So unidirectional, for the unidirectional the signal is going to present for the t equal to 0 to infinitive. This is initial, this is final. Okay. So now the initial value theorem we proved. Now we go for the final cases. That means I write for the x of infinitive. Final case of the signal I represent as x of t. That's right. I wrote for the x of infinitive. So finally, what will be going to represent? Final value of function x of t is represented as infinitive. That is directly from its Laplace transform of x of s, without the need for finding the inverse Laplace transform of x of s. First, we go for the statement. The final value theorem of Laplace transform state that x of t Laplace transform is equal to x of s. Then limit t tends to infinity, x of t is equal to x of infinity. Then limit s tends to 0, s into x of s. This is called for the final value theorem. Next we go for the proof of final value theorem. From the definition of final value theorem, using for the unilateral Laplace transform, we use Laplace transform of x of s equal to 0 to infinity x of t e power minus st dt. So this one is represented as a unilateral. The unilateral we know already discussed in the initial value theorem. So it starts for the 0 to infinity only. The time is going to start to 0 to infinity. You take then next step we go and take for the differentiation with respect to time on both sides. So that is L d x of t divided by dt is equal to integration of 0 to infinity d by dt x of t e power minus st dt. As per the time differentiation property, if we take for the differentiation in the signal of x of t, that the Laplace transform is consist of s x of s minus x of 0 minus in the Laplace transform. Now I adapted for this value into this location. Okay. So what will be happen? So Laplace transform of d x of t divided by dt is equal to integration of 0 to infinity d by dt x of t e power minus st dt. This value, that is a first differentiation, we got for s x of s minus x of 0 minus. Okay. Now we should apply for the s tends to 0 in the limit on both sides of the above equation. Limit s tends to 0, integration of 0 to infinity d by dt x of t e power st dt is equal to limit s tends to infinity s x of s minus x of 0 minus. So this integration of 0 to infinity d x of t dt into dt, these two are getting to cancel. Now limit s tends to 0. These two are getting to cancel. Finally, what will be going to happen? We got for the x of t integration limit of 0 to infinity, that is equal to s tends to 0 s x of s minus x of 0 minus. Now this interval we substitute for the our all removed cases. Automatically what will be happen? D by dt is getting to cancel. Finally we got for this notation only. There is no action for this t, but integration is there. So but that limit is represented as 0 to infinity. Then limit s tends to infinity s x of s minus x of 0 minus. You substitute for the limit x of infinity minus, first limit is infinity, maximum limit minus of x of 0 minus equal to limit s tends to 0 s x of s minus x of 0 minus. Now the x of infinity is equal to limit s tends to infinity x of s. Now we got for the final value theorem. So this initial value is equal to 0. Okay, initial value is equal to 0. Therefore we have limit t tends to infinity x of t is equal to x of infinity equal to limit s tends to infinity x of s into s. This is called for the final value theorem of Laplace transform. Next we go for some numerical example. First determine the x of t and then verify the final value theorem of function. Here also I take for the x of s equal to 1 by s plus of 3. The given function I should write as x of s equal to 1 by s plus of 3. Taking the inverse Laplace transform. We know the inverse Laplace transform of 1 by s plus of a is equal to e power minus at. Okay. So in the term of a, here we used for the 3. That's why inverse Laplace transform of x of s, okay, equal to x of t. So inverse Laplace transform of x of s equal to x of t. I wrote here that x of t is equal to Laplace transform of what we are going to receive, that is 1 by s plus of 3. So we know a in terms of this formula, a in terms of 3. That's why I wrote for the result is e power minus 3t. That means x of t equal to e power minus 3t. I wrote here x of t equal to e power minus 3. Then the final value of given function is x of infinity is equal to x of t tends to infinity is equal to e power minus 3t, t tends to infinity. Then we should apply for the t tends to infinity. What is going to happen? Then x of infinity equal to t tends to infinity, where the t is there, you can substitute for the infinity in the e power. So finally we got for the e power infinity equal to 0. Then using the final value theorem, x of infinity is equal to limit s tends to infinity x of s into s equal to limit s tends to infinity, that is s tends to 0 s into 1 by s plus of 3. The finally I represent as a x of infinity is equal to limit s tends to infinity 1 by 1 plus of 3 by s equal to 0. The final value theorem of given function is proved. Okay. So now we prove for the both the final value theorem as well as a initial value theorem. We taken for the some example. That example also both we take similar only, but this case both example also we proved for the final as well as a initial value theorem together. Both the example we taken for the same x of s representation. Okay, that is equal to 1 by s plus of 3. So next we go for the relationship between Laplace transform and Fourier transform. If x of t is a continuous time domain function, then the Fourier transform is given by f of x of t equal to x of omega is equal to integration of minus into plus into x of t e power minus j omega t dt. If x of t is a time domain function, then the Laplace transform is defined as limit x of t is equal to x of s, then integration of minus into plus into x of t e power minus st dt. Here s is called for the complex variable. It's given by s is equal to sigma plus j omega. The Fourier transform of continuous time signal x of t I described as x of omega integration of minus infinity x of t e power minus j omega t dt. Okay. Now I need to prove of this relation. Now this Fourier transform I should take for the inverse Fourier transform. That is Fourier transform of x of t is equal to x of omega. So you take for the inverse Fourier transform of x of omega is equal to x of t. So that's why generally we write as x of t, the Fourier transform is x of omega. Okay. Now this inverse Fourier transform I need to write. The inverse Fourier transform of the given signal is represented as x of t 1 by 2 pi integration of minus into plus into x of omega e power j omega t d of omega. Now I replace for the omega by sigma plus j omega in the definition of Fourier transform. So omega, where the omega place is there, I substitute for the sigma plus j omega. Now x of sigma plus j omega is equal to integration of minus into plus into x of t e power minus sigma plus j omega t dt. The inverse Fourier transform of x of t I should write x of t is equal to 1 by 2 pi integration of minus into plus into x of sigma plus j omega e power sigma plus j omega t dt. Now I tried for the term sigma plus j omega is equal to s in the case of inverse Fourier transform condition. That means what will be happen? I need to find for the differentiation because d omega is there. Okay. So due to that case, then sigma plus j omega is equal to s. This is a constant. That's why there is no problem with differentiation. So I should differentiate. Then what will be happen? J d of omega equal to d of s is there. So j equal to d of s divided by d of omega. I need for the d of omega. That means d of s divided by j. I write. So here d of omega equal to d of x divided by j. So these terms are need to substitute for this equation. Now what will be happen? X of s equal to integration of minus into plus into x of t e power st dt is there. Then x of t is equal to 1 by 2 pi j integration of sigma minus j infinity sigma plus j infinity x of s e power st d of t we write. This equation is known as bilateral Laplace transform pair of or complex Fourier transform pair. For the Fourier transform is equivalent to the Laplace transform evaluated along the imaginary axis of s plane. Then x of omega equal to x of s, s equal to j omega. The Laplace transform of function x of t is equal to Fourier transform of x of t multiplied with e power sigma t. Now I write for the Laplace transform x of t is equal to Fourier transform of x of t e power sigma plus, that is e power minus sigma plus t. That is Laplace transform of x of t is equal to f of x of t e power minus sigma t we wrote. Okay. Then difference between Laplace transform and Fourier transform. First we go for the Laplace transform, that's we go for the Fourier transform in the table. The Laplace transform of a function x of t can be represented as a continuous sum of complex exponential damped wave of the form set. Okay, but the Fourier transform of the function x of t can be represented by continuous sum of exponential function of the form of e power j omega t. Okay, so this is not said, is represented as e power st. So here I write the Laplace transform of x of s equal to integration of minus into plus into x of t e power minus st dt. But Laplace transform x of omega is equal to integration of minus into plus into x of t e power of minus j omega t dt. So this term I represent as a continuous sum of complex exponential damped wave of the function of e power st. See the Laplace transform e power st. That minus minus common, we can leave it. So this portion only we take first point. The Fourier transform also same like that one. What is it? So the continuous sum of exponential function of the form of e power j omega. Next case. Both Laplace transform and Fourier transform is applied for solving the differential equation only, that related to the input and output of the system. Okay, both the transform, it's going to possible to do the solution of differential equation in the terms of the system it's going to take for the input and output. Next case, the Laplace transform can be used to any unstable system, but the Fourier transform is cannot be used for any unstable system. It's always going to give the solution of stable system only. Next difference. The Laplace transform does not require that the function is defined for a set of negative real number, but Fourier transform not for doing for the negative real number, but it will be going to do for the all real numbers. That means I should say that Fourier transform is only defined for the function that are defined for all real numbers. Next case, Laplace transform exists for every function with Fourier transform, but the Fourier transform, it is not always true that every function with the Laplace transform has a Fourier transform. The next difference, the Laplace transform is widely used for solving the differential equation, since the Laplace transform exists even for the signals for which the Fourier transform does not exist. But Fourier transform is really used for solving the differential equations, since the Fourier transform does not exist for many signals. For example, mod of x of t, as it is not absolutely integrable. The Laplace transform has a convergence factor, and hence it is more general. The Fourier transform does not have any convergence factor. The Laplace transform of the signal x of t is equivalent to the Fourier transform of the signal, that is x of t e power minus sigma t. The Fourier transform is equivalent to the Laplace transform of evaluated along the imaginary axis of the S-plane. These are the difference between the Fourier transform as well as the Laplace transform. Then we go for the some example of Laplace transform. Now I take for the signal f of t equal to u of t. Find the Laplace transform. Now u of t, we know the values. What is that u of t? U of t is unit signal in the continuous cases. So that is equal to 1 when t is greater than or equal to 0, 0 otherwise. I should draw for the graphical representation when this is a t. Okay, t both it will be have the negative side. This is represented minus negative side. This is 0, t equal to 0. Then value is equal to 1. That means here. So after that one, it will be up to infinity. It will be represented as 1. This is u of t. So remaining portion all will be represented 0, 0. Otherwise I write. This is a graphical representation. Then we need to find for the Laplace transform of f of t equal to f of s. Okay, this value I represent for the Laplace transform of u of t. This value I should write as Laplace transform of 1. U of t is equal to 1. The limit is present for the 0 to infinity 1 into e power minus st dt. I write for the term here. Okay. After doing the integration, first it will be do for the differentiation e power minus st divided by minus of s. The lower limit is 0, upper limit is represented as infinity. Okay. So then substitute for the lower as well as upper limit. So here is e power infinity is represented as 0. Then you substitute for the 0 for e power 0, that is equal to 1 by minus of s. This minus getting to cancel. Then we got the 1 by s. The Laplace transform of u of t, the signal is represented as 1 equal to 1 by 2. Okay. Up to this much, I'm going to stop this session. We'll see for the remaining example in next session. So I refer for the books are Signals, System and Communication for B. Lathix and A.V. Openham. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.